Okay, good morning. Welcome back. Happy Wednesday. I've got a couple of announcements to make, but we're missing some folks, so I'll make those announcements in just a minute when people trickle in. Today, according to the calendar, the arbitration project is due, so go ahead and throw that project into the green folder. I will say that I do accept projects late according to the syllabus. If you turn it in at some point between now and the start of our next class, it is 5 points off. If you turn it in after that, it is 10 points off. I will only take it up to 1 week late. So after 1 week from this moment right now, it is 100 points off. You don't want to be in that position. So I see some people frantically trying to finish up this project. So it is an easy decision for you whether you turn it in now or take the penalty. If you think you can earn at least 5 points between now and Friday by continuing to work on this project, then you keep the project and you turn it in and you take the 5 points off. But if you think you are fiddling around with less than 5 points worth of stuff, throw it in the green folder as is. Any questions on that? Okay, so everybody's making a decision right now. Project in the green folder at this moment is on time. Project in the green folder like 10 minutes from now is late, so throw it in there if you want it without a penalty. Yes, please. Yeah. Okay, so what we're going to do today is something called interpreting derivatives, and we'll look a little bit at notation. Also coming up on Friday, the trucks project is due. And then Friday will be our last day of new material before test one. Monday is our review day for test one. I don't have any new stuff we're going to talk about on Monday, just a review day. And the test is Wednesday. Hunter. A review sheet, did you say? Yeah, like, or not. Good question. So you don't have to go there now, but on page 80 is where we're going to talk generally about the test number one. And then on page 83 is a very detailed list of things that I think you need to be able to do to be successful on test number one. And then starting on page 84 is a collection of sample test problems, all of which have videos of me solving them up on YouTube. So there are lots of resources available. Okay, good question. Any other questions on the schedule? Okay, so I think that is that. All right, so next thing I wanted to talk about is the quiz. So I'm just giving the quiz back to folks who came in a minute late here. Okay, does everybody have their quiz now? All right, so the results of the quiz were quite good. And even if your particular result was not up to your standards, the quiz is worth less than 1% of your course grade. This is supposed to be a low stakes way to get feedback right now. The test is a high stakes way to get feedback. And so you want this feedback now to know, hey, I'm where I need to be, or hey, I need to do some work or study differently or make some change in order to get where I need to be before Wednesday's test, okay? If you have individual questions about the problems on the quiz, then see me individually. I'm free right after class every day. I'm free right before class every day. Come find me, talk to me. What I don't want you to do is just take this quiz, throw it in the folder, and never look at it again. It's feedback. Take a look at the stuff that you missed. Figure out how to do it. If you need help figuring out how to do it, I'm available. Your classmates are available. Math Studio Peer Tutoring. But also take a look at the stuff that you did right and make sure that you're solid on it. I mean, maybe you did it right, but you were kind of like fuzzy and you were hoping it was right, but weren't sure. So that's a moment to also take the feedback I gave you and say, okay, yeah, that's exactly how I need to do this in the future. All right. Just a couple of general things about the quiz. So first of all, I took off like half a point maybe for folks who are missing labels. Like if you just took a derivative but didn't label it with an F prime, then you lost half a point. I used to take off more points a year ago when I taught this course. I took off more points and I got some feedback from a bunch of students that said, hey, Ian, I get it. We need to write things with correct notation, but it feels like taking 1 point off of a 5-point problem because of notation, that's like a 20% deduction, and that doesn't feel appropriate for the the calculus knowledge I have. I'm just not writing it in 100% the right way. So I backed off on how much I take off but don't interpret that to mean I don't think it's worth anything. Like that little -1/2 is my way of getting your attention and saying, hey, you got to start writing this stuff more clearly. And trust me, I am more stubborn than you are in terms of notation. And so you got to make a choice. If you lost some points on this thing for notation, then you can choose to lose the same points again on the next test and maybe the next quiz and maybe the next test after that. Or at some point you can say, I don't want to lose any more points for notation. I'm going to learn how to use the notation and then I'm going to use the notation. And this notation thing is bigger than our class. This notation thing is about effective communication, and you guys are pursuing associate's degrees and certificates, and improving your communication skills is part of my job here. And so this I see as part of the bigger picture of communicating effectively. And quite frankly, some of you are going to have bosses that are really dumb, and you need to make sure that you like convey information in a clear and effective way so that this person who somehow rose to the top of the ranks understands what you are talking about, okay? So make sure that you don't leave me guessing there. Just label. I'm not talking a lot of writing, not a lot of ink, but label things. Don't let stuff float. And so just a couple of examples here. We're on page 66 if you missed that. But if you have some function like square root of x, and I say take a derivative, and you need to first rewrite that in a better form, like x to the 1/2, give me an equal sign. Equals connects one thought to the next one, okay? Don't just let it float. That doesn't mean anything to me. Is that f? Is it f prime? Is it something entirely unrelated? I don't know, but these two little lines make it very clear what that is. That is still f. And then when you say, okay, and the derivative is 1/2 x to the negative 1/2, just call it something. Right now it's not called anything. What should it be called? It should be f prime, right? It's not a lot, but now it is crystal clear exactly what you have done. And then if for some reason you had to plug x equals 2 into the original, so you did something like, I'll make a different number, 9. You had to plug x equals 9 into the original. 9 to the 1/2, that's really the square root of 9, which is 3. But how do I let the reader know I have plugged 9 into the original? What is that symbolized as? Plugging 9 into the original. That is f of 9, right? That's what that is. 9 to the 1/2 is out of left field. F of 9. Ah, okay. I see what thought you are starting. And if you had to plug 9 into the derivative, 1/2 9 to the negative 1/2. How do we symbolize that? That's f prime of 9. So it's just these little tiny symbols on the left-hand side. It's not a lot in terms of writing, but it's a heck of a lot in terms of communicating effectively. Also, there were places where there was one problem where you had to take your derivative and set it equal to 0. Can somebody tell me there was like some factored thing on the top of the back? 3, what was it? X, all right. X minus 4, x plus 2, right? So we had this thing. And some people went right from there to x equals 4 and x equals negative 2. They're not connected at the moment. Again, this is out of left field. What did you do to this equation to decide, hey, x equals 4, I'm sorry, to this expression to decide x equals 4 and x equals negative 2 are important? You turned it into an equation. What equation? Equals 0. That's all you got to write. But without the equals 0, they're not at all related to each other. Okay, that equals 0 is mandatory. I started taking points off for somebody who didn't put the equals 0. And then as I continued to grade the quiz, I said I'm taking points off of like half the people in the class. So I did not do my job. So I didn't take any points off for this one. But I will if you omit it on the test. Equals 0. If you are solving, if you are bringing equals 0 into the problem, just write it. Right? Doesn't take long. Okay, I think just equals 0 and then x equals 4 and negative 2. We're good to go. Okay, yeah, and then, like just finally, like you don't want me trying to figure out what you did when I have a red pen in my hands. That is a bad time for you to be not, for me to be not sure of what you did, okay? So just write enough so that it is clear to me, the reader. Sometimes I can figure it out and I'll give you the benefit of the doubt and I won't take anything off, but the harder I have to work to figure out what you did, the more likely that red pen is gonna come out, okay? All right, so let's move on to class number 10. In this class, we learned different notation for the derivative, and we explain what the derivative represents in a variety of contexts. This section is very notation heavy, but stick with it. These unfamiliar symbols will become second nature for you with some effort. So, brief history lesson. Calculus was invented / discovered independently by two folks, Sir Isaac Newton there on the left, and Wilhelm Gottfried Leibniz on the right. Isaac Newton from England, Leibniz from Germany. Both discovered this field independent of each other right around the exact same moment in time, right around 1660 AD. And it might sound unusual for two people that had hardly any communication with each other to come to exactly the same conclusions and create this massive field that we now call calculus. But it actually was fairly common in math for this to happen. Calculus was discovered by these two gentlemen, but calculus was not just like a flash out of the blue. Calculus had been building for 2,000 years. Like Archimedes in ancient Greek was doing some calculus stuff 2,000 years ago. And it's a long course through math history, going from, like algebra to like thinking about rates of change. And finally, these two guys are the ones that put everything together. But it was this tower that was almost complete. They just happened to be the ones that, both sort of figured out how to get that top piece put into place. One of these gentlemen you've heard of. I'm assuming you have not heard of Leibniz, which is really a shame because they both should get pretty much equal credit for this discipline. It turned into a pretty ugly battle in terms of like who the rightful discoverer of calculus was. Like while these two guys were alive, it was ugly. They didn't really publicly come out and say, it's mine and it shouldn't, don't give the other guy credit, but they had supporters. And the support kind of went down like nationalistic lines, like people in England were for Newton, people in Germany were for Leibniz, and it was not a pretty scene in mathematics. Ultimately, you guys have heard of Newton and not Leibniz, so you can sort of see how things went, but they really deserve equal credit for this thing. Newton goes down as like one of the greatest mathematicians, physicists of all time, right? He's got stuff associated with gravity and relativity, like the beginnings of that kind of thing, right? You can trace like from Einstein all the way back to Newton. There's a direct line there. He's knighted, right, over in England, Sir Isaac Newton. He's buried with honors in Westminster Abbey. Like tons of people, go to his funeral. Leibniz is buried, and one person goes to his funeral. It was his secretary. So it was like these two guys did like exactly the same thing at exactly the same time, and sadly had very divergent paths for the ends of their days. Okay, so they use different notation for the derivative. Newton wrote the derivative of x squared plus 7 as x squared plus 7 with a dot on the top. We have not adopted Newton's notation for the derivative. Leibniz used notation that we do use. Dy over dx was his notation for the derivative. And he used that to represent the derivative of y with respect to x. And he was thinking about the formula for slope, not a calculus thing. Delta y over delta x is something you've seen for years now in math class, and it's just the slope. And he just took that idea of slope of a line and generalized it to the slope of a point, slope at a point for some curvy thing. And we've talked about how, secant lines morph into the tangent line. So dy dx is supposed to be very reminiscent of delta y over delta x. In fact, delta is the Greek letter for what? D. I mean, it's the same, right? It's just like Latin D versus Greek D. About a century later, the French mathematician Joseph Louis Lagrange invented the symbol f prime of x for the derivative. We will use f prime of x and then this d over dx thing exclusively throughout the course. Four things that all mean the derivative. F prime of x on the far left, y prime on the far right, Leibniz's dy over dx here. And then if we just kind of generalize this a tiny bit, y is really just another name for f of x, right? And so these two symbols in the middle, they mean the same thing. All we're doing is changing a y to an f of x. And so hopefully this gives context to a symbol that I introduced over the last couple of classes. I said if you see d over dx, that means take a derivative of whatever's in the bracket. It's just like a dy over dx. Okay, one disadvantage of Leibniz's notation is that writing f prime of 3 is awkward. So we talked about this last class. Dy dx, vertical line, x equals 3 means take 3, plug it into the derivative. So we're going to do a lot of contextual interpretations of the derivative today. And I think it's really important to think about what the units are. I'll give you lots of different scenarios. If you know what the units are for the derivative, you're halfway home to understanding what the derivative means in that context. So the dy dx has units of the form y units over x units, which again makes an awful lot of sense if you think about slope, right? Delta y over delta x, it is clearly y units on top. I'm subtracting some y's, and then x units on the bottom. And so it's exactly the same for the derivative. Y units on the top, x units on the bottom, or more generally, dependent variable units on top, independent on the bottom. So number 6, if g of t represents the cumulative number of gallons of water that have passed over a waterfall t seconds after midnight, then dg dt, that is the derivative of that function with respect to time, has what units? Okay, so let's get them over here. Units on top are the g units. What are they? That is gallons. And units on the bottom is seconds. So the units for that derivative are gallons per second. Gallons per second. And very often we're going to translate that division line to the word per, because that just makes it easier for us to understand what the thing means. So in that context, let's figure out what each of these things means. So the one says g of 30 equals 120, and the other says dg dt evaluated at t equals 30 is 3. So let's go with this first one. This 30 what? That's 30 seconds. After what moment in time? 30 seconds after midnight. Okay, so 30 seconds after midnight. And then this 120, what are the units there? That's gallons, just plain 120 gallons. So 30 seconds after, 30 seconds after midnight, 120 gallons had fallen over this waterfall. Cumulative, that is a total. It's not like a one moment in time. It's just in those 30 seconds, 120 gallons went over the waterfall. And then we're going to write a sentence for this other equation. So this is a derivative. It is evaluated at t equals 30, the same t equals 30. So we're still talking about 30 seconds after midnight, but something is equal to 3. What are the units here? Gallons per second. That's what we talked about. G, T. They're in the same order, really. I mean, you just have to copy the units in that order. G on top, T on the bottom. So something was happening 30 seconds after midnight. Something was changing at 3 gallons per second. You probably have a sense, I mean, this is just like water going over the falls, right? So it was going over the falls at 3 gallons per second. We have the advantage of understanding how waterfalls work in this problem, but you're going to see some context which you don't have like any history with. And so I would just say this cumulative number of gallons is changing at 3 gallons per second, right? The cumulative total number of gallons is changing at 3 gallons per second. That is clearly more awkward than what we all know is happening. The water's flowing at 3 gallons per second. But just in case you don't know, like you don't really have a history with the context, you can always just say that dependent variable cumulative number of gallons is changing at 3 gallons per second. Okay, so I will say something in between those two. At t equals 30, the number of gallons going over the falls is changing at a rate of 3 gallons per second. And when I ask you to interpret on the first test, you got to make sure you include the 30 in there. Don't just tell me water is flowing at 3 gallons per second. There's a specific moment in time that references. It's 30 seconds after midnight, right? It doesn't say anything about what's happening 31 seconds after midnight or 28 seconds after midnight. It's just at that one moment in time. Okay, so let's take things up a notch. Suppose that r is equal to dg dt. That is the derivative of the g function. And now we're going to take a look at the units of the r dt. That is to say the derivative of that function, which itself is already a derivative. Okay, starting to feel a little bit dicey here because we're sort of 2 layers into this. But let's see if we can start by writing down the units. So the units for dr dt. What are the units upstairs? Units upstairs? R, what is R measured in? Gallons per second. Those are the units for R. Gallons per second is just the units upstairs. Gallons per second. That's R. Over T. What are the units for T? Seconds. So something is changing in the unit gallons per second. And so if I give you some numbers and I say the r dt at t equals 20 is -2, so 20 seconds after midnight, the rate at which the water is going over the falls is changing. This is another rate, right? Like the rate itself is changing. There's really 2 rates going on here. The rate at which the water is going over the falls is changing at -2 gallons per second. Does this mean the water is going backwards, like up the falls? What does it mean? It means what? Yeah, it's slowing down, right? Still going over the falls, but not as fast. It's not -2 backwards. It is slowing down. It's losing like 2 gallons per second. Still going over. And maybe if it was like 10 gallons per second, and then you lose 2, okay, now it's only 8 gallons per second. Still going over, just not as fast. Okay, so if we write a sentence here, I think I said it, the rate at which water is going over the falls is decreasing by 2 gallons per second. And then I'm going to say each second. You could say 2 gallons per second, or for every second. It's totally fine, but I just kind of want to separate. So, yeah, they don't cancel. They're actually working together. This would be gallons per second squared if you wanted to smush them together. Yeah. So again, we've got a history with waterfalls, and so we understand. Like I could use different words that make this like clearer. Actually, the first function, that g function, is like the position of the water. This 3 gallons per second, that's a velocity, right? It's a speed of the water. This -2 gallons per second, it's an acceleration, right? The water is slowing down, still going, still moving positively, but slower and slower. So we do have like distance, velocity, and acceleration. But I'm avoiding those words because we normally don't have like special words, right? I'm going to give you lots of different contexts. Okay, so I think that is good. Oh, I lost a point in my sentence. What did I leave out? Something I told you. At t equals 20, right? At t equals 20. Yeah, all we know is that one moment in time. All right, so there are 2 activities. They are wildly different from each other. The first one is lots of writing sentences and interpreting in context. The second one has to do with a lot of graphical interpretations of derivatives and slopes and things like that. Before you jump in, Dadrian had an announcement she wanted to make.